All right. The idea of an absolute max or min is covered in 3.3. That's just the mechanics. How do I actually find the highest or the lowest point for a graph? And then applications of that. Are any scenario where we want to find a max or min? Okay. Our basic, they're called optimization problems. Okay. Well, we talked about how last time that not every graph over its entire graph can have an absolute max or min. We did talk about a special case. We gave an example of one that did. It is something like the quadratic. It has increasing all the way on one side, increasing on the opposite side. And so that local min is the absolute max or min. So we said a special case is if I have 1. If our model has 1 critical point, and it ends up being a local extrema, then it is the max or min, it's the absolute max or min. Alright. Okay, but let's say we don't have that special case of an example of something that has an absolute min over the whole graph. We said if we're just looking at a specific window, then we know where it does have an absolute max or min. If we restrict our graph to just a specific window, okay, then it will have a max or an absolute max and min. Right, and we talked about last time, we stressed figuring out where it happened, and so what did we find out last time? Where can they possibly happen at? What was that? Does anyone else remember? Local max or min, good. It happens at either the endpoints or the local extrema in the window. Alright, so the steps for if we ever have a problem. Okay. For example, okay, let's make it. let's say we had f of x is okay. We want the absolute extrema in the window one to 5. Okay, so we know that absolute extrema, they're either going to be at the endpoints or it might be at one of the local extrema in the window. So to just get the answer, all we need to do is find out, okay, where could I possibly have local extrema? It would have to be at a critical point. So the first step is find the critical points. Okay. An absolute max means it's the highest point in that window, and absolute min means it's the lowest point in that window. So then the second step would just be to actually brute force it. Plug in the endpoints and the critical points in the window. The highest value number is the absolute max, the lowest value number is the absolute min. Right, so our conclusion, right, the largest value is the absolute max. And the smallest or the lowest value, absolute min. Alright, so like for this example, first step we get the critical points, we need the derivative, so what would you get from that? Minus 12. You want to solve this equal to 0 or undefined. Alright, and so what will you get as a critical point here? Okay, x equals 2 is our critical point that's in our window, which is going from 1 to 5. If I got another critical point that happened at 0, right? It's a critical point, but does that matter for us in terms of the window we're looking at? Anything outside of the window we can just ignore. And so the second step is compare the x and y values. Okay. I have my endpoint, I have my critical point, and I have another endpoint. Okay, I'll plug them into the original, get the y values for each one, and then I'll see which gave me the biggest, which gave me the smallest, and then I make my conclusion from there. This one you get minus 2? And then if you put in 2?
7. No, wait.
Negative 5, and then when you put in 5, $22. Alright, so then what can you tell me from here? Okay, this is our absolute max. Here we have our absolute min. In terms of application, what is this saying? We have an absolute min of minus 5, and it happens at x equals 2. We have an absolute max of 22, and it happens at x equals 5. Okay. So finding absolute max or min in a window, that's all the steps you have to do. Right? Questions with how it works? Yeah. We talked about that with kind of like this visual here. We know an absolute max would be the highest point on our graph, and absolute min would be the lowest point because it goes on forever in both directions. I have to look at a specific window and I can make that conclusion. So, for example, here we had our absolute max, our highest point. Here on this point, the endpoints actually seem to be the same for the lowest point. And so really we're just comparing y values in terms of which is the highest, which is the lowest visually. And algebraically we'd be looking at the y values here. Yeah.
So we solve for the critical point and it's not in the window, and there's no...
You don't need to worry about it. Exactly. So like you solve for a critical point and it's not in the window, would look something like this. You're looking at a window right here. There's no critical point here. The extreme values would probably be at the endpoints in that case. Okay. So application problems. Right. I have a whole handout for you all with different situations. I'll do 2 different examples. They're mostly going to be centered either around like some business or geometry problems because that's the kind of common denominator we have in this class. So for example, something you might see is, aside from a straight up, I give you the model, like the equation and a window and tell me absolute max or min. I'll do a couple examples where you have to do a little bit of work actually putting the equation together. So let's say you want to build a rectangular fence. You want to build a fence, a rectangular region. Okay. You went to Home Depot, you had a limited budget with their sale and everything, you only buy 80 feet of fencing. Okay. Whatever reason why you have this constraint, that's what you're dealing with. You have 80 feet of fencing to do the job. What dimensions would maximize the area of this yard? Alright, so here we have to do a little bit of work because we're not given any equation. We want to optimize something because we want to find the maximum of something. We want to maximize, in this case, what? Okay, so we want to optimize or we want to maximize area. So our objective, our goal, is this area of our yard. Okay, it's rectangular, so what do I know about the dimensions of this? Exactly, so let's say that I'm calling this length and the width, they're both the same on opposite sides. Alright, so in terms of my area equation, what does it look like right now? L times W? Alright. What are my limitations though? I'm trying to optimize a 2-variable equation, right? I have 2 moving parts to it. I know how to get a maximum when there's 1 moving part or 1 variable. What else am I given? I have a constraint. I have some limitation. I don't have unlimited supplies and an unlimited budget to make this yard. I'm limited by what? Good. right? My fence has to go around each of the 4 sides and add up to, it can't be more than that 80 yards of fencing that I have. All right. Okay. Again, we said if I could write this equation with one variable, I know exactly how to optimize it. I get a maximum by taking the derivative, finding a critical point, and then going from there. The problem is that I have 2 variables. What are some ideas to make this into a problem we know how to work with? Alright, so I can use this limitation I have to solve for one of the variables, replace it in my area equation. To get a 1 variable equation. Okay, so let's say we solve for L. Okay, and then last step, what does L look like? Okay, so I'm dividing everything by 2, I'll get 40 minus W. Okay, now I'm going to plug this into my area equation. So I have area equals, instead of L, I know that this is 40 minus W. Okay. Now it's one equation with one unknown. Okay. And so in terms of getting a maximum, what would you do from here? Yeah. Right, we'll do the derivative of our area equation. What will you get on the right-hand side? Okay. Right? To find where max happens, I need to get critical points and then check if it's max or min. Okay. Right, what do you get for the critical point here? Okay, W is equal to 20, that's our critical point. Alright, we're asking to find the maximum of something without looking at a window. We know how to find a maximum. Why will, if this ends up being maximum, why will it be the maximum? There is no window, so how come it works when there's no window? Will it be the max? How many critical points do we have? It only has 1, right? So if it's a maximum, then it's the maximum. Okay, but I need to check if it's a maximum, right? So we have 2 options. Remember we did this on the quiz? 2 ways I can check if something's a maximum. What's one option? Sign chart? What's another option? Second derivative test, right? So 2 options to check if it's a max or min. We could either do the first derivative test, which we'll look at the sign chart. What is the derivative doing for any number smaller than 20 in terms of the sign? What's the number smaller than 20 we can check? 10. If you plug in 10, what will you get for the derivative? 20, a positive number? Okay. How about anything bigger than 20? 30. I'll get 40 minus 60. So what's the sign of the derivative? Negative. So what can you say about It's the max, okay? Second derivative test, how does that work? Into what? Into the second derivative. So let's get the second derivative. What's the second derivative here? Careful. -2. Alright. No matter what, over this whole graph, no matter what the variable is, what's the concavity always? It's always concave down, right? Bless you. Concave down at a critical point. What does that mean is happening? That it's a max. It's concave down everywhere, including the critical point. So it's a max. Let's see. Alright, so since I only have one critical point, and it's a max, it is the maximum for the graph. Okay, the max area happens at W equal to 20. Okay, well, but the thing is I have two different dimensions here. I have a W and I have a length. So how can I figure out the L? Plug in, right? L is equal to 40 minus the 20 that we had here. So it's also 20. Right? Alright. Okay, any questions with this example, how it worked? Yes?
I don't know the question how it works, but then now you just can start.
Yes. Yeah.
That one always got me. I remember this problem from last semester.
Yeah.
But I feel like I should just remember the answer at the beginning. I want to yell, 20.
No.
But this is a totally different way to find it than the
Exactly. Yeah. So you might look at this problem and think it's really easy. I could have predicted that, but that's not the point. These are our training wheels. This is how to do the mechanics of it so that when we get harder problems, we know how to do it, right? Another example that you could see with the word problems where this is if you have to write your own equation. So let's say we have a car rental business. So a car rental business finds that it can rent 60 cars if it charges $80 for a weekend. Okay. But they want to play with the prices. They know that, like, if you increase the price, yeah, you get more money, but then you'll probably have less people willing to rent your car. So they want to find the sweet spot of, okay, what price should I charge to get enough rentals where I'm making the most amount of money. So it estimates that for each $5 increase, in price, they get 3 less car rentals. What price should they charge to maximize the money they bring in? Mm-hmm. And how many cars are they renting out when they do this? All right, so we want to try to figure out how to model this scenario. What seems to be the moving part? What's the thing that's changing? Okay, the price is changing. Every time we go up $5, what's the relationship we have? It's going down 3 cars, right? So right now, our revenue looks like this. If we don't change anything, right, revenue is price times the quantity that you're selling or the service that you're providing. Right now, if we don't change anything, if I charge $80, we're going to have 60 cars rented out. Okay? What's another relationship we have that we can say?
I would say 80 plus 5 equals 60 minus 3.
Good. Okay, so if I move up my price one time, I'm gonna get 3 cars less. What if I move this price up twice? What will happen? Right? If I were to change it 3 times, right? If I were to change the price an X amount of times, right? What would I fill in here?
6 minus 3.
Okay, so I'm using this to model my situation. What exactly does X mean though? Just for the record. So the revenue is the price times quantity. So here I had basically a 1 for X, right? I moved up the price one time and I had to pay that penalty. I moved up the price twice and that was the penalty we got. If I move it up an X amount of times, so what does X represent?
Price increase.
The number of times we're changing the price, right? It's the number of $5 price increases. Alright, so then I want to maximize that. Again, I'm not given a specific window, so right now what we know how to work with is if I have one critical point, then I know it's for sure the absolute max or min, if I can check that it's a max or min, because I don't have a window. But that involves finding the critical points first. Either you can distribute and like collect like terms, or we still know how to get a derivative with it written like that. What can you do to find that? Product rule? What would you get for the derivative here? This guy is going to stay the same. What will you get here? Alright. Okay. Now it's just algebra solving this equation equal to 0. There's nothing that will make this undefined, so I have nothing to worry about here. But distribute, so this will be, what, 300 minus 15x minus 240 minus 15x. Okay. And so adding like terms here, what will you have? Okay, equals 0. And so then x is equal to 2 is our critical point. Okay, this is still our first derivative. Alright, we have one critical point. If it is a maximum, then it is the maximum. We have 2 ways to check. What way do you all want to opt for? Second derivative test. So you'll get to see which one is easier given this situation. So we want to check okay, what do you get for the second derivative here? Negative 30, right? So it's concave down all the time, including at our critical point. So what can you say about it? Yeah. Sorry. So then it's a max. is where the max happens. Okay. So in terms of answering the question, what's the price we need to charge and how many cars are we going to rent out for the maximum revenue, what would you say? Good. So $90 to rent, and then 54 cars are rented out for maximum revenue. Exactly. Because we want to know what price and how many cars. So this is our price, 80 plus 5x, and that's our quantity. All right. For the rest of class, I'm going to have this handout that I'm going to ask you all to work on. This will be a really easy way to get 100% quiz grade, because what I'm going to have you all do is working in groups of 2. You're going to work through different problems. In the last half hour of class, I'll tell you which problem you need to turn in. And so each group will be given a specific problem to turn in. We'll go through the answers together. And by turning that problem in correctly, that gives you 100% for today's classwork, and that goes as a quiz grade. All right? So it's a spring break gift. All right. Yeah, you'll have like half an hour to make sure it's not wrong.